Welcome back, Physics 30. This is the second video in the length contraction section. So we looked at the derivation of the formula, looking at movements of objects, etc., and how length contraction comes into play. We were looking at this painting example. So a person on the spaceship seeing a painting on the wall, the painting just simply doesn't change because it's moving along with the person. It's not moving relative to the person, so it stays the same. But someone on Earth seeing the spaceship move with the painting, of course we apply the length contraction, and again, if the spaceship is moving left to right, it's the left-right portion of this painting that will contract, so the 1.5 meters. So the regular part of the painting is 1.5 meters, 90% speed of light, and so when we apply that, 0.65. So we can see that the painting has shrunk or contracted in the left-right motion down to 0.65 meters. So the picture has the dimensions 1 meter, not by 1.5, but by 0.65. So that's extremely funky how that happens. If you look at another example here, a fantasy super train, a very fast train with proper length of 500 meters long, as measured by people at rest on the train. So they see the train, yeah, it's 500 meters. It's passing through a tunnel that's 200 meters long, according to the observers on the ground. Let us imagine the train speed to be so great that the train fits completely within the tunnel as seen by the observers on the ground. That is, the engine is just about to emerge from one end of the tunnel at the time the last car disappears in the other end. What is the train speed in order to do this? So here, the train itself is contracting such that it fits in the tunnel. As wacky as that sounds, it can happen if the train is going fast enough. So since the train just fits inside the tunnel, its length measured by the person on the ground has to be 200. Okay, so the train we know is 500, but we need it to shrink down to 200. So of course we look at the length contraction formula. So this time we're looking, the train's proper length is 500. We want to shrink it down to 200. So all we have to do with this equation is solve for v squared. Okay. No, I don't think. No, I didn't do this. So they do skip steps here, but it's a fairly relatively easy to do this. So of course, when I get v by itself, so that means getting the radical by itself. Divide by 500. Divide by 500. We get 0.4. And then to get rid of the radical, they squared both sides, so we get that. So there's basically two steps here missing. Divide by 500 and squaring, but they mention it there, so it's relatively easy to see. So if we bring the v squared over c squared over to the other side by adding and subtracting by 0.4, we get this. And then of course square root to get rid of the v squared and the c squared, we get that. 1 minus that, and then of course we're going to multiply by the speed of light, 0.92c. So hopefully you're okay with that. The text tends to skip steps from time to time, assuming you know what to do there, so hopefully you're okay with that. So if the train is traveling 92% of the speed of light, or 0.92 times c, it'll shrink down to 200 meters in that direction of motion. Now, of course, yeah, there's a few notes here. No train can go this fast, but yeah, if we could go that fast, that would in fact happen. An observer on the train would not see the two ends of the train inside the tunnel at the same time. Recall the observers moving relative to each other do not agree on simultaneity. So that's an interesting thing to note. An observer on the train would not see the two ends of the train inside the tunnel at the same time. So according to someone sitting down watching the train go by, wow, that train fit inside the tunnel. But the people on the tunnel would say, no, our train is still extended out. So again, they would not see that in fact happen. And that kind of leads to exercise C here. What is the length of the tunnel as measured by the observers on the train itself? So what would the people inside the train see? So someone outside the tunnel sees the train moving inside the tunnel, or seeing the moving train, but the people on the train see the tunnel moving. So what is the length of the tunnel itself? So I've worked that over here. So of course the proper length of the tunnel itself is 200 meters, as we were told in the original question. So the length of the tunnel going 90, now the train people in the train see themselves as standing still, and it's the tunnel that's moving past them. So the tunnel will be contracted according to people on the train. That's the wacky part of this question. So we get that, so 0.92 squared, we get this. C squared over C squared cancel out. Boom, 78.3836 meters, but 200 has one sig fig, so round 78 off to 80 meters. So the people on that 500 meter long train see the tunnel being 80 meters only. So they're saying something completely different. And again, simultaneity is not agreed upon because of the high speed these guys are going at. Lastly here, resolving that train tunnel fiasco, how weird that is. Observers at rest on Earth see a very fast 200 meter long train pass through a 200 meter long tunnel. So even though the train was 500 meters, people on Earth or at rest see that train contracting down to 200 and fitting exactly in that tunnel. So the train momentarily disappears from view inside the tunnel. Observers on the train measure the train's length to be 500 though, because according to them they're at rest and it's the tunnel moving by them, and they see it to be 80 meters long. So clearly a 500 meter long train can't fit inside the 80 meter long tunnel. How is this apparent inconsistency explained? So again, events simultaneous in one reference frame are not simultaneous in another. Let the engine emerging from one end of the tunnel be event A, and the last car disappearing into the other end to be event B. To observers in the Earth's frame, A and B are simultaneous. So A is inside, B is inside. To observers on the train, however, the events are not simultaneous. In the train's reference frame, event A occurs before event B. So in other words, as the engine emerges from the tunnel, observers on the train observe the last car to be still 500 meters minus that 80, 420 meters from the entrance to the tunnel. So people on the train don't see that they are entirely in the tunnel. According to them, there's still a lot of train yet before A emerges from one end. Okay, so that is the length contraction section. It's very similar to time dilation, except it's really an inverse equation there. Rather than time getting longer for people on Earth, so with time dilation, time is longer for people on Earth as opposed to the moving object. Here, the length is not longer, but smaller for the people witnessing this event compared to the actual length. All right, we'll see you again.